We're going to talk about vectors today. All a vector is, if you ask most people that have seen this before, they say, oh, a vector is something that has a magnitude and a direction. And they're exactly right, but that gets a little confusing. What you actually want to think about a vector is just a stick. Really, that's it. At least for our purposes. Now, it does have a much more complicated definition, but for most of the things that we're going to deal with vectors, the idea of thinking about it as a physical thing that has a length and a direction is pretty helpful. So, and I'm just going to say something with a magnitude and direction. Okay, so that's the actual definition, something with a magnitude and a direction. But if we're thinking about this in terms of, say, a stick, now this stick can be a two-dimensional stick, say it's lying in a plane, or it can be three-dimensional out here in space. It has a magnitude, it has a specific length, and it has a direction. Now the direction when it's out here in 3D space is a little bit more complicated. We'll get to that in a day or two. But in two-dimensional space, the direction we're going to do is we're always going to measure this from the positive x-axis. So think about the horizon, so to speak, as being here. The direction is always going to be the angle measured from there to the positive x-axis. Now, since a vector basically is just a stick with a length and a direction, the nice thing about that is the length doesn't change depending on where it is, and the direction, since we've decided to always measure from the horizon, I can draw this stick, the same stick, absolutely, kind of the same, absolutely anywhere. So we say that vectors are generally independent of their coordinate system. There's a lot of different ways that we can talk about that, but it's really just the same stick. Now, the symbol so to speak, that we do for a vector is we draw a ray. Now, a ray is wrong, because remember, a ray has a starting point but goes on forever. That's not what a vector does. A vector has an initial point and what we call a terminal point, which means it ends. This does not go on forever, right? It's a stick. It has a specific length. Now, the arrow at one end shows that we started here and went to there. So every vector has this terminal point and initial point. The easiest way to describe a vector is generally something called in component form. Now, component form is a nice way to represent a vector. Let me kind of draw one over here. Kind of the way that we would think about giving directions for somebody here. If we started here and say, how do I get from the initial point to the terminal point? You'd say, we walk this much in, say, the x direction and that much in the y direction. So what we're going to do is we're actually going to give this as an x piece and a y piece. Now, let's talk about some notation here, because it can be a little confusing compared to what we write, compared to what textbooks use. Most of the time for vectors, we use lowercase letters. And the letters we generally use for them are like U's and V's. So I'm going to start out with a U here. Now, the book here is just going to use a bold lowercase letter to represent a vector. Since we can't write in bold, we need another notation. Now, the actual notation of this is something that looks like a vector. So technically, you're supposed to draw a little tiny arrow above it to show that it's a vector. However, mathematicians are pretty lazy people, so instead of drawing the entire arrow, we just draw half of it, because you can do that in just one swipe. So that's how we're going to denote a vector. Here's the vector U. Now, we want to show that it's different than a point, so I don't want to do something like this, say that it moves in an x direction and a y direction, because that looks exactly like a point, and I wouldn't be able to tell them apart. So instead of writing it like that, I'm going to use pointy brackets like this. Now, again, we are going to say how much it moves in an x direction and how much it moves in a y direction. And of course, a three-dimensional vector, if I were to do the same thing, would have an x component, a y component, and a z component. Now, if you're given a terminal point and an initial point to find the vector, it's always going to be the terminal point minus the initial point. And we'll see an example of that in just a second. So if you're given the terminal point and initial point, to find the vector, it's just terminal minus initial. Now we do run into a small problem with this type of notation because in a lot of math that we were going to run into, we end up with more than just 3 dimensions. So if we have x, y, and z, what do I use next? And what if I have 10 dimensions or 20 dimensions? So instead of using this as our naming convention, a lot of times we switch to something like this. Since the vector's name is u, I'm going to name all of its components u as well. I'm going to just label them using subscripts, u1, u2, u3, so on and so forth, for ever how many components that it has. Now the convention though here is u1 is still the x direction, u2 is the y direction, u3 is the z direction, and then after that you kind of have to define what the other dimensions are that you're talking about. So this is the standard notation that we're going to use for the rest of the semester, but just realize first component is the x direction, second component is the y direction, third component is the z direction. So let's try a quick little example of how to find a vector for given a terminal point and an initial point. So let's say if I said find the vector with initial point 2, 3 and terminal point -4, 6. Okay, so we're going to name this vector anything you want. I'm going to name it v because that's another common letter. Remember, we always do the terminal point, -4, 6, minus the initial point. Now here's an operation we've never done before. We've never subtracted or added points together before, so how do you do it? Well, the good news is it works exactly like you would think. We're going to subtract the x's and subtract the y's. Now, I'm going to change this real quick, because once we subtract them, this is no longer a point. So I can't use the parentheses here anymore. I need to use the brackets to denote that this thing is now a vector. So this is now going to be the vector -6, 3. Now, of course, if we wanted to represent this vector visually, all you'd have to pick is any starting point. Even though we're told, you pick this as the starting point and that is the initial one if you wanted to draw it from there. But this vector, remember, you can pick up and move anywhere you want. So if you had any other arbitrary starting point, you could still draw this vector. That says move -6, 6, and up 3. So that would be that vector drawn just anywhere. Now, for convenience, a lot of times we do draw these things starting from the origin. So if we draw this starting from the origin, it's called drawing it in standard position, just like we would do with your angles back in trig. All right, so component form is the most useful form for our vectors, but it's also helpful if you're given a component form to be able to find its magnitude and its direction, because that's what a vector really is. So let's talk about the magnitude and direction. Right, the magnitude and direction of a vector. So let's say I gave you an arbitrary vector here, u1, u2. Now we're going to start in 2 dimensions and see that everything just kind of scales up for 3 dimensions here. So if we have the vector u1 and u2, think about if I sketch this from standard position. I'm just going to assume it points over here somewhere. So that's my vector u, which means it moves some distance in the x direction u1 and some distance in the y direction we would call u2. So if I wanted to know how long that stick was, all I'd have to do is use my Pythagorean theorem. So if I wanted to know the magnitude, and we'll see what the notation is for that in just a second, all we'd have to do is what? This squared plus this squared equals the length squared, or the square root of u1 squared plus u2 squared. Now our notation for magnitude here is going to be like our absolute value, but you put an extra bar on it. So that's the notation for magnitude. You kind of got this double bar. Now, believe it or not, it's really the same symbol, and I don't know whether or not the magnitude gained a bar or the absolute value lost a bar, because it actually works exactly the same way. Because a one-dimensional vector would just be u1 squared, and you take the square root of it. So if u was just, say, watch, -2, then the magnitude of u would be the square root of -2 squared. That's the square root of 4, which is 2, right? And we all know the absolute value of -2 is positive 2. So it works as the absolute value as well. Now, what if it was a 3-dimensional vector, or 4-dimensional, or 5-dimensional? Well, the good news is our magnitude scales also. So if it's a 3-dimensional vector, it would be u1 squared, u2 squared, u3 squared, so on and so forth. No matter how big the vector gets, that's just your magnitude. All right, let's talk about direction here. Let's do direction. All right, for the direction of a vector, again, I'm going to draw the same picture we have right over there. There's our vector u, which means it has a u1 and u2 component, an x component and a y component. Now, the direction that we're talking about, remember when we started this is for a 2-dimensional vector only in this case because it has to be flat on the board. We said that the direction was going to be the angle measured from the positive x-axis. So how do we figure out what theta is here? Well, remember, if we know what the vector u is, we know what u1 and u2 are. So from trig, we know the relationship between the angle and those two sides is the tangent of the opposite over the adjacent. Now you have to leave it like this. And here's where it gets a little tricky because trig can be a little tricky. We could solve this and say theta is equal to the arc tangent of u2 over u1. The problem is this may not be the right answer. This is always the right answer. This may not be. Because remember, when you do the arc tangent, it can only give you an answer in the first or fourth quadrant. So if theta actually is in the second or third quadrant, this here is going to give you the reference angle, and you're going to have to add 180 degrees to it. So let's try an example here, and you can see what I mean. I'll sneak a calculator out here in a second. So if I said, find the magnitude and direction of, let's say, u is equal to -2, -3. Let's start with the magnitude. That should be pretty straightforward. The magnitude of u is going to be the square root of -2 squared plus -3 squared, 4 plus 9, or the square root of 13. Okay, so there's the magnitude. If we're going to talk about the direction, I know the tangent of the angle is going to be the u2 over u1 or the y over the x. So -3 over -2 or 3/2. Now again, to get to our answer, again, I'm just on the calculator real quick. We do have to find the arc tangent here. I'm going to do this in degrees. So if I did the arc tangent of 3/2, just by doing this, the arc tangent of 3/2 gives me about, let's say, 56.3 degrees. Now, you should be able to tell that this answer is wrong, because if I ask you to sketch this in standard position, if I were to sketch this in standard position, the vector -2, -3, that's -2, -3, that points down there into the third quadrant. So that's in the first quadrant. So you can see that that angle's wrong. And you can definitely tell because the x and y are both negative. So what we actually ended up with here, we ended up with this angle, 0.3. That angle right there. So notice it's, for the arc tangent, it gives you the angle that's straight across from it. So the actual answer here, theta is going to be 56.3 degrees plus 180. So what's that, 136.3 degrees? Okay, so if your original vector points either into the second or third quadrant, you have to add 180 degrees. So if the vector points into the second or third you need 180 degrees or pi, depending on what your units are. All right, let's do one more thing here. We've seen now that if we're given a vector in component form, we can find its magnitude and its direction. Well, when you're given a magnitude and a direction of a vector, you're actually given what's called polar form. Here you're given the magnitude and direction. As you see that we were able to find if it was in component form, we can actually find polar form very easy. Most of the time when you're given application problems, you're actually presented a vector in polar form. It tells you the magnitude and the direction of it. Unfortunately, doing arithmetic in polar form is very, very difficult. So what we want to do is actually go from polar form to component form. So how to get to component form. All right, so let's draw our picture again and see if we can figure it out. Now this time, instead of having, let's say that we have some vector u here. That's still our vector u. Well, what are we given? Well, in this case, we're given the magnitude of u, and we're given, now here's a notation that you will see in a lot of textbooks. Since this is the angle for our vector u, a lot of them will use a subscript and say that that's the angle for the vector u. So you will see that from time to time. To be honest, I'm not sure if your textbook's using it or not. So how could I figure this out if I know that side and I know this angle there? Remember, what are we trying to figure out? I want to know what u1 and u2 equal to if I'm going to get this into component form. Excuse me. Since I'm looking for two things, let's go after them one at a time. Let's go after the x first. So what relates these three things? The two things I know and the one thing that it doesn't. Again, we're in a right triangle, and you can see that the sine of that angle, and I'm just going to use theta right now, is what? The, excuse me, cosine. The cosine of that angle is the adjacent over the hypotenuse, which is just the magnitude. So by solving this real quick, you can see that the first component is the magnitude times the cosine of that angle. And if we did the same thing over here, instead of looking for the x value, let's look for the y value. You can see that the sine of the angle would be the opposite over the hypotenuse. And again, solving for u2, you can see u2 is the magnitude times the sine of the angle. So we actually have our answer now. So our vector u in component form is going to be the magnitude times the cosine of the angle and the magnitude times the sine of the angle. All right, now believe it or not, this is something that you should have already known or at least seen before. Because at least in your trig class, you should have seen this. Remember our unit circle? When we're on the unit circle, that means, of course, a circle with radius 1. Every point on that circle was the cosine of that angle and the sine of that angle, right? If we came to here, this point was given by the cosine of the angle, comma, the sine of the angle. Well, if we're on the unit circle, that means that this radius here, you can kind of think about it as your vector. That means that that vector would have a magnitude of 1. And notice if you put the magnitude of 1 in here, you end up with, well, your unit circle out of this. All right, we've got a lot more to talk about vectors, but I think that's it for this time. We're going to come back and finish up the basic concepts for all these things.